Hello everyone, this is Prakash Shrestha. I'm currently working as a postdoctoral associate at the University of Florida. Today I'm here to present our work through this pre-recorded video. Specifically, I'll be talking about our IvoriWatch system, an integrity verification scheme for the web based on a wearable device. So why do we need this integrity verification scheme for the web? It is because modern computing paradigm allows the user to perform various sensitive operations through web interfaces. For example, almost all banking institutions allow bank transactions through websites. An email can be composed either through website or client application. Further, safety critical devices such as medical devices like pacemaker, blood pressure sensors, and smart home devices like security camera, voice assistant devices can be configured through web interfaces from a host machine, typically a desktop or a laptop PC. Given the highly sensitive nature of these application scenarios, it is very important to protect the user input or the request originating from the host machine from manipulation. It is typically easy to secure the communication link between the host machine and the remote server through cryptographic mechanism, for example, the TLS SSL. However, the host machine itself often gets compromised with a Trojan or a malware that can allow an attacker to manipulate the user input at will. The compromised host machine is one of the biggest threats in the computing paradigm, and manipulation of input from such compromised host machine, it can lead to severe consequences, including financial loss, damage of reputation, security breach, and even put human lives in danger. Let's look at an instance of input manipulation attack. Consider a host machine which has been compromised with a banking Trojan, say GS, that can manipulate the user input. When a user attempts to transfer a fund from his account to the another account, the Trojan it can manipulate the amount and destination account number. Typically, before completing the transaction, it prompts the user to approve the transfer by sending a confirmation notification to the user's phone. However, as the user was intending to transfer the fund, he may approve the transfer without paying much attention to the details on the notification, resulting in the illegitimate transfer of funds to the attacker's account. Given the severity of input manipulation attack, as noted earlier in this paper, we propose IvoriWatch system, a transparent integrity verification mechanism for the web that can verify whether the request or the input received at the remote server it has been modified or not. Our scheme is based on wearable device, which can be a smartwatch or a bracelet that typically comes with motion sensors. In IvoriWatch, when the user provides input to the remote server, two series of data are generated. First, the input itself from the web application, and second, the motion sensor data from the watch. IvoriWatch verifies the integrity of user-provided input by correlating these two data points. If these two data points do not match, it flags that the input might have been manipulated by a malicious actor and takes proactive actions, for example, by not responding to the current request and alerting the user through some sort of out-of-band mechanisms. In our threat model, we assume that the host machine has been compromised with a malware or a Trojan that can manipulate the user input. We also assume that wrist-wearable device using IvoriWatch system is secure and hasn't been compromised. We consider two adversarial scenarios. In the first scenario, we assume that the user is actively providing input to the remote server using a compromised client, and the malware that has infected the host machine, it tries to manipulate the user provided input at will to harm the victim or to gain benefits. In the second scenario, we assume that the user forgets to log out his web account. The adversary, utilizing this opportunity, attempts to supply a fabricated input. In such scenario, the malware doesn't have any clue about what the remote victim might be doing. Based on real life activities, we consider various activities that the victim might be doing when the malware tries to provide its fabricated input on behalf of the user. For instance, we consider a scenario where victim is using terminal at a remote location. We also consider that the user is using phone for browsing internet, texting, or for other purposes. Further, we consider that the user is writing on a sheet of paper or walking on his regular pace. We even consider that the user is having a regular conversation with his colleague, friend, or family while standing or sitting on a chair. We refer these activities as miscellaneous. Now let's see how IvoriWatch works at its core. We divide the keyboard characters into two regions, left and right, as shown in the figure based on the hand that is typically used to type the given character. When a user provides input to the remote web server, IvoriWatch generates two sequences: actual sequences of keyboard regions corresponding to the input and a sequence of keyboard regions predicted based on wrist motion captured by the watch. IvoriWatch correlates these two sequences to verify the integrity of the input. Let's assume that the similarity threshold is set to the 70%. For the given input, the two sequences matches by more than 70%, indicating that the input is legitimate. If these two sequences do not match, it raises the flag indicating that the input might have been modified. In IvoriWatch, key region predictor is responsible for inferring the key's region, whether it is left or right, based on the motion sensor data from the watch. IvoriWatch extracts several statistical features as listed in the table from motion sensor data. To evaluate the performance of IvoriWatch in the benign as well as in the adversarial settings, we collected data samples from 20 graduate users. We used the practice test website that offers online typing and data entry relations. It provides text on diverse topics and a place to type in those texts. We asked the participants to type in the provided text on the given website freely for 10 minutes while wearing watches on both hands. 20 user sessions then resulted in 20 data samples, each consisting of three traces: input or the text from the terminal, motion sensor data from the left hand watch, and the motion sensor data from the right hand watch. To evaluate the performance of IvoriWatch in the user aware setting, we randomly selected two participants and asked them to perform each of the 5 different activities considered in our threat model for 5 minutes. In our evaluation, we considered 3 different settings based on the hand in which the user wears the watch. Users may wear the watch either on the left or the right hand, so we consider left hand and the right hand scenario, where we use the features extracted from only left and right watch respectively. We also consider a scenario where users wear the watch on both hands. This scenario is exploratory, as users generally wear watch on only one hand. In the future, we may expect users having wearable devices on both hands, watch on the one hand and the other type of bracelet on the other hand. We consider only the input having a length of at least 5 characters, but it can be a combination of words with variable length. From the input text collected from the users, each word and corresponding motion data from watches was segmented. For the evaluation purpose, n number of consecutive words were combined in a sliding window fashion so that we can form a variable length input. We employed leave one subject out cross-validation approach in our evaluation, where for the input text from a given user, keyboard region predictor was built using the samples from all the other users. This indicates that our predictor is user agnostic. To evaluate the overall performance of IvoriWatch, we use false negative rate, which indicates the error rate at which legitimate inputs are identified as manipulated inputs. Similarly, we use false positive rate, which indicates the error rate at which manipulated inputs are identified as legitimate input. We also computed equal error rates, which is an equilibrium point of FNR and FPR. Now let's see the performance of IvoriWatch. This figure shows the variation of FPR and FNR for a very similarity threshold for the left-hand setting. We achieved an EAR of 0.15 at a similarity threshold of 0.61 in this setting. The EAR increases to 0.23 in the right-hand setting at a similarity threshold of 0.58. We were able to achieve an EAR as low as 0.13 at a similarity threshold of 0.62 in the both hand settings. This indicates that combining motion data from both left and the right hands improve the performance of IvoriWatch. This figure shows the performance of IvoriWatch in user-aware setting, where the malware supplies fabricated input on behalf of the user when the user is performing a random regular activity. In this setting, we achieved EAR of around 0.15 at a similarity threshold near 0.60 in all the hand settings. Since the length of the input may have an impact on the performance of IvoriWatch, we proceed to evaluate such effect in both the benign and attack settings. As we saw earlier that we achieved EARs for different settings at the similarity threshold close to 0.60, therefore we set similarity threshold to 0.60 to measure the variation of performance with different input lengths. This figure, it shows the performance of IvoriWatch as a function of input text length for both hand settings. As can be seen from the figure that both FNR and FPR decreases on increasing the input text length from 5 characters to 100 characters. You can see a slight increase in FPR as the text length tends to reach 100 characters. We attribute this to the decrease in the amount of benign and attack samples that affect the computation of FPR. We observe the similar trend in both the left and the right hand settings. Concluding this presentation, in this work we introduced the IvoriWatch system, a transparent integrative verification system for the web based on wrist-wearable device. Our results show that IvoriWatch can identify legitimate input and detect manipulated input with minimal errors. The performance of the scheme can further be improved by leveraging wrist wearables with a higher sampling rate of motion sensor data, for example 500 Hz or more instead of 200 Hz used in our current implementation. Like any other study, our scheme has certain limitations. The scheme was evaluated with only 20 graduate students. Future work is needed to evaluate IvoriWatch with a large and diverse pool of participants. User may use different personal devices other than desktop PC used in this study, for example laptop, mobile phones, and tablets, to provide input to the remote server. IvoriWatch can be easily extended to laptops since the layout of the laptop keyboard is almost similar to that of the desktop PC, although the size differs slightly. We believe that wrist gestures generated when using laptop would be similar to those when using the desktop PC. IvoriWatch may also be extended to support mobile phones and tablets by tweaking its algorithmic designs. Rigorous future work would be needed to explore more in this direction. That's all. Thank you for attending and listening to my talk. If you have any queries and concerns about our work, I would be happy to answer them. Thank you.